Today we'll be discussing logarithms. So logarithms are basically what I perceive as the inverse of exponents. So any logarithmic function you can also write exponentially. And you'll see right here, log base a of n is equal to x, can also be written as n is equal to a raised to x. So there's a logarithmic form and an exponential form. Notice that we have two special logarithms here, the common logarithm and the natural logarithm. The common logarithm is log of base 10. Notice here, there's no little number there, so log without a little number is assumed to be base 10. So we have log of n is equal to x, means that n is equal to 10 raised to x. On the other hand, we have the natural logarithm, and that's base e, Euler or Euler's number. So ln, we depict natural log as ln. Ln n is equal to x, it means that n is equal to e raised to x. But even though we have specific ones, they all work the same way, they just have a different base. These are some of the properties of logarithmic functions. So the product property, notice that we have log base b of m times n can be rewritten as the sum of two different logs. So we keep the same base, log base b of m plus log base b of n. That's when it's multiplied together. It makes sense that for the quotient property, it's the opposite, right? So we have log base b of m over n. We're going to now keep the same base, but subtract the two logarithms. For the power property, if you have your number raised to a power, we can bring that to the front of the logarithm and multiply it. Lastly, the property of equality just means that if you have the logarithm of the same base of two different variables and they're equal to each other, then the variables are also equal to each other. Notice that here it's given on the right examples that you're able to look at. So feel free to press pause and then take a look at them, but we will be going through some examples together. Okay, now we'll go into some examples. Use the definition of a logarithmic function to rewrite each equation in exponential form. And for this one, we're going to be using what we were told in the first page of this. So we have log base a of n is equal to x. We can rewrite in exponential form, which would be n is equal to a raised to x. So for this letter A, our n is 81, our a is our base, which is 3, and the exponent is going to be 4. So for me, when I'm trying to do this, I just try to remember, first of all, that the base of the logarithm, that little 3, is going to be the base of the exponent as well. So we'll rewrite this. So we have 4 is equal to log base 3 of 81. I know 3 is going to be my base. 81 is that n, and my exponent is 4. So I always switch from side to side. 3 raised to 4 is equal to 81. Or you can rewrite it as 81 is equal to 3 raised to 4. It's the exact same thing. And this is true. 3 times 3, 9, 27, and 81. For letter B, we have negative 2 is equal to log base 3 of 1 over 9. Our base is still 3 here, but our exponent is now negative 2, which is equal to 1 over 9. And I know this is true because 3 raised to negative 2 is 1 over 3 squared, or 1 over 9. So we're not solving anything, we're just rewriting. We'll move on to solving the next one. Now we see some solving stuff. So what we're going to do is rewrite it in exponential form, and then from there, solve for x. We rewrite letter A. Log base 4 of x is equal to negative 2. So I know I'm going to rewrite it with my exponent being 4. So we have 4 raised to negative 2 is equal to x. And 4 raised to negative 2 is 1 over 16 is equal to x. Oftentimes, I actually don't even set up the equation like that. I just do the inverse. So for me, the inverse of log base 4 is to raise 4 to whatever that is. So that's what I would do. So I have this. Log base 4 of x is equal to -2. I would just raise both sides to that exponent. So I have 4 raised to that, 4 raised to that. And this 4 raised to something will cross out or cancel out the log base 4. So I'm left with x is equal to 4 to the -2, which is 1/16. We got the same answer. Either way should be fine. Now look at these other ones. So letter B, we have log base 25 of x is equal to 1/2. So you can do it either way. Maybe I'll just set it up. So we have x is equal to 25 raised to 1/2. I know that just means I'm taking the square root. So x is equal to 5. For C, log base 3 of 7 minus x is equal to 3. You can set up the equation, or you can just raise 3 to each of these. So setting up the equation, I'll have 7 minus x is equal to 3 raised to 3. Solving for x, we have 7 minus x is equal to 27. Subtracting that 7, negative x is equal to 20. So x is -20. And I do suggest that you guys actually check your answers for each of these using a calculator, just because maybe you're not so familiar with using logarithms yet. So it's something that you do want to be checking your answers just to make sure. And to do that, I would just plug it into here, the original equation, and then make sure that it makes it true. And let me just show you what you would be putting in your calculator, because you're not going to be able to put it in different bases in your calculator unless you have a pretty advanced one. So what you would do, say for example, you wanted to check this letter B in your calculator. In your calculator, you would put, let me just indicate here, it's in the calculator. You would put log (5) over log 25 equals, and you should get 1/2, because basically you're trying to check log base 25 of 5 is equal to 1/2. This is what you would put in your calculator, and it should equal to 1/2. For letters D and E, we'll set it up again. So notice that we don't have any bases that are shown here, right? So log without a base, we know it's going to be base 10. So for this, I'll write 10 as my base. Raised to -1 is equal to 1.34 minus x. From there, 10 raised to -1, I know it's just 1/10, which is 0.1. Solving for x, subtract that 1.34. We're left with -1.24 is equal to -x, which gives us 1.24. And again, you should be checking this in your calculator. And for this one, you could just put log of 0.1 should be equal to -1. And lastly, we have this one, our natural logarithm. So ln 2 minus x is equal to -1.4. For this one, I know the base is going to be e, so I know I'm going to have base e raised to -1.4 is equal to 2 minus x. Using this in a calculator, e raised to negative 1.4. So e raised to 1.4. We have 0.247 is equal to 2 minus x, subtracting 2. 1.753, but make it negative, is equal to negative x, which gives us x is equal to 1.753. This is one that we should check in a calculator, so I'm actually going to check it. So I'll check ln of 2 minus 1.753, 2 minus 1.753, take the ln of this, negative 1.398. Close enough for me. So we're good. Now we're going the opposite way, so we're writing the equation in logarithmic form. I know I'm going to keep that same base, so for this one, I'll rewrite as log base 5 of 125 is equal to 3. And for this, if you want to check it again in a calculator, you can put log of the bigger number, 125, divided by log 5. And then in your calculator, that should give you 3. Looking at this next one, I'm going to have the base of 9, so log base 9 of 3 is equal to 1/2. Okay, so we just went the opposite way that we did before. So now we're going to use some of the properties that we had discussed before. We have the multiplication or the product property, quotient, power, and then that's what we have for these ones. For A, I'll be using the product property. For B, we have the quotient. And for C and D, we'll be using the power property. So product, quotient, power, and power. So for all of these, notice that we don't know what x, y, and z are. However, we do know what log base A of x, y, and z are. So we want to separate each of these so that we just have a logarithm of any one of them. So we have log base A of yz for A. I'm going to separate it into 2 different logarithms, one of just base y, or one of y and one of z. So we have log base A of y times z. Because of the product property, I know it's just going to be a sum of logarithms of y and z, both base A. So log base A of y plus log base A of z. And we do have an equation for log base A of y, which is 1.8. Log base A of z is 2.7, which would give us 4.5. That was letter A. Okay, for letter B, let's use a different color. Log base A of z over y. We now have the quotient, so we're just going to subtract our logarithms. So log base A of z minus log base A of y. Log base A of z is 2.7. Log base A of y we know is 1.8, which gives us 0.9. Just separate these. For letter C, we're going to use the power now. So we have C log base a of y to the 6th power. I know I can rewrite that and bring that power to the front. So we have 6 times log base a of y. Log base a of y is 1.8. 6 times 1.8, it should be, using a calculator, 10.8. Now moving on to letter D, another power. But for this one, it's not expressly written as a power, so I'm just going to switch this to a rational exponent. So we have log base a of z raised to 1/3. I know cube root just means raised to 1/3. So I'm going to bring that over to the front. 1/3 times log base a of z, which is 2.7. Which gives us 0.9. It's important to note that just because these are both 0.9 for letters B and D, they're not always going to equal. They just happen to be equal for this instance or this situation. So in the last one, we were kind of expanding in order to evaluate. So now we're going to look at rewriting and condensing into a single logarithm. So for this one, we have both. We want to make sure that they're both of the same base so that we can add them together. If we have two logarithms with the same base added together, we can just instead rewrite it as keep the same base, a logarithm of the same base of the two different ones, the expressions multiplied. So we have log base 3 of x plus 1 times x minus 1. And I already know this is going to multiply out to, you can either FOIL it, or if you already know, this is going to be x squared minus 1. And whenever you do have an expression, you do want to keep it in parentheses. For letter B, we'll do the same thing. Now notice that we have a power here. So we want to actually, let's move this first to be an exponent right there. It's base 10. This is the common logarithm. 2x plus 1 minus log of x plus 1 raised to 1/3, or you can take the cube root. And then from here, we'll just divide. Log of 2x plus 1 now over, you can use the cube root of x plus 1. If you left it as raised to 1/3, that's fine. And from here, we can actually just leave it. Okay, now that we have a single logarithm for each side, we're good. Okay, now moving on to the last few problems, we now have an exponential form. So we can solve it by converting it to logarithmic form. And I want to also show you the way that I usually do it by using the inverse. So say, for example, if I have 7 raised to 2x, I'm working on this letter A. 7 raised to 2x is equal to 823,543. So for me, what I typically would do, I would just take the logarithm of each side, but keep the same base, the base that we have there. So I want to keep the base 7. So in order to take the inverse of 7 raised to 2x, I would just do log base 7 of this, log base 7 of this. And this would cancel out. So I'll be left with 2x is equal to log base 7 of 823,543. If you wanted to go the other way and then just set up your equation using the exponential to logarithmic equation that's given in the beginning of this video, then you can do that as well. But you'll notice that you'll get the same answer either way. So you keep the same base, log base 7 of that should equal to this. You'll get the exact same equation. From here, you can evaluate this using a calculator. And again, in the calculator, you would input log of 823,543 divided by log of 7. And inputting this into your calculator will give you 7. So 2x is equal to 7. Divided by 2, we have x is equal to 7 over 2, or 3.5. And again, you should check this in your calculator. So you just 7 raised to 7, or 7 over 2 times 2, will be equal to 823,543. Trying now letter B. 0.05a is equal to a times 1.06 raised to negative x. Notice that we have two different variables in this equation. We cannot solve if we have two different variables. So actually, when you see that a is multiplied to each side, I'm just going to divide each side by a, and that would actually cancel them out. Now I no longer have to worry about a. 0.05 is equal to 1.06 raised to negative x. Again, I already know I can just take the logarithm base 1.06 of each side, or I can set up that equation. So I already know I'm going to keep that log base 1.06 of 0.05 is equal to negative x. From there, using your calculator again, log of 0.05 divided by log of 1.06. And this gives us negative x is equal to negative 51.412. So x is equal to 51.412. You should check this again using the calculator. So 1.06 raised to negative 51.412. And using a calculator, it should give you 0.05. C and D now. 75,000 is equal to 15,000 times 1.02 raised to 4x. We already know we want to just be isolating x. So first thing I'm going to do is move this 15,000 to the other side by dividing it. $75,000 divided by 15,000 is 5. So we have 5 is equal to 1.02 raised to 4x. I'm going to take the logarithm of each side of base 1.02, or just set up that equation. It's going to be 4x is equal to 1.02. Oh, sorry, logarithm base 1.02 of 5. And evaluating that logarithm using a calculator, you'll get 81.274. Dividing that by 4 is 20.318. This is something that I would definitely check in a calculator. Again, I know I keep saying it, but always check your work, especially when you're dealing with logarithms. Okay, last example, we have letter D. 2,500 is equal to 600e raised to 0.05x. So again, I'm going to move that 600 to the other side. 2,500 divided by 600 is going to be 25 divided by 6. I might leave it as a fraction for now. E raised to 0.05x. I already know I'm going to take logarithm base e. We do know that that's just going to be ln. the natural logarithm. So we have ln of 25 over 6 is equal to 0.05x. So for this, we'll just take the ln of 25 over 6. And this is 1.427. 0.05x dividing by 0.05 is 28.542. And guess what I'll suggest now? Check it in a calculator. And that covers our lesson for logarithmic functions. I hope it's nothing too crazy. Be sure to do the practice problems and good luck.